This is Physical Science 1, Chapter 4, Part 1 on the laws of motion. In this portion of the video lecture, we will be discussing the first two laws of motion, as well as introing a discussion of gravity. Since we know now the basics of motion, forces and acceleration from our last chapter, we can now kind of do a little bit more of application to see how motion applies in the real world. Of course, Newton's laws were developed by Sir Isaac Newton. Using math that was fairly advanced for the day, he was able to state rules that describe the effects of forces on the motion of objects. Newton's first law of motion is also called the law of inertia. It basically states an object moving at a constant velocity keeps moving at that velocity unless an unbalanced net force acts on it. So basically, objects will keep doing what they're doing. If an object is moving, it's going to want to keep moving. If it's at rest, that object is going to want to stay at rest because it's going to take an unbalanced force for it to change whatever it was previously doing. So inertia, remember, inertia is a property of matter. So it's the tendency of an object to resist any change in its motion. It's kind of like the laziness of physics. So if something is moving, it's going to want to keep moving. For example, if you're driving in a car and you, of course, have your seatbelt on and the driver slams on the brakes, okay, your body continues to move forward until the seatbelt stops you from doing so because your body as an object in a moving car wants to keep moving. So it's the law of inertia. Likewise, if you're in that car, if the car is in park and then the driver throws it into drive and punches on the gas, your body falls backward. And that is because your body was at rest and it wanted to stay that way. So unless an unbalanced force acts on an object, objects will keep doing what they're doing. If an object is moving, the velocity of that object remains constant, again, unless a force changes it. Inertia is going to be related to its mass because remember, inertia is a property of matter. So the greater the mass of an object, the greater inertia it will have. Now there's some more science terms that we have to discuss between mass and weight. A lot of people use those words interchangeably. Again, however, they mean different things. Mass is the amount of matter that an object has, and its weight is the amount of mass that it has plus the force of gravity acting on an object. We use the unit of a Newton to calculate weight. So force is calculating using units of meters per second squared and kilograms or grams. So these units combine to form a mass and acceleration unit that we call a Newton. So Newton's second law of motion has to deal with acceleration. Newton's second law states that the acceleration of an object is in the same direction as the net force on that object. In other words, we can calculate the acceleration of an object if we know its net force in newtons and we know its mass in kilograms. So we can calculate acceleration a couple of different ways now. We can take a look at initial and final velocities, like we did in our last chapter, or we can also take a look at force and mass to calculate acceleration. So again, the unit that we use is called the Newton, named after Isaac Newton himself, so that's a capital N. So these here are the three different ways that our acceleration equals force over mass equation can be played, depending if you want to find a force, an acceleration, or a mass. Now remember, we also can accelerate or calculate acceleration by taking final velocity minus the initial velocity over the time. So now for some of our physics math problems, you may have to solve for acceleration first before dividing by the force. So the acceleration of an object is going to depend on its mass as well as the force exerted on it. So just to make sure we know the difference between mass and weight, an object will always have the same mass, the same amount of matter, no matter where that object is. So in other words, mass always stays the same. An object's weight, however, because that's mass plus the force of gravity, can be different in different places in the universe because different forces of gravity exist. So basically, a translation of that is weight can change. If I weigh myself here on Earth, and I am 61 kilograms here on Earth, I can go up to the moon, and on the moon, I would weigh 10 kilograms. However, I still have the same amount of mass, but because the moon has 1/6 less gravity than Earth does, my weight will change going from the Earth to the moon. If I went to Jupiter, I would be, well, offhand, I'm not sure the calculation, but I would be probably over 100 kilograms of weight if I went on Jupiter, because the gravitational force of Jupiter is much, much stronger than that of Earth. But again, I have the same amount of mass. So mass stays the same, weight can change. So let's talk about gravity. Gravity is what we call the attractive force between any two objects. And the reason why we discuss the difference between masses and weights is because gravity is going to have to deal with the mass of an object and it's the distance between them. So if you increase the mass of an object, you are going to increase its gravitational force. So large objects have a very high gravitational force. Small objects have a very small gravitational force. If you decrease the distance between objects, you will increase gravitational force. So in other words, the closer two objects are, the more gravitational attraction those two objects will feel. The further apart they are, the less gravitational forces are there. We call gravity a basic force. There's the big four of the basic forces. Also along with gravity, we have the electromagnetic force, the strong nuclear force, and the weak nuclear force. But gravity is universal. Gravity exists everywhere in the universe. It just depends on how much. So we can calculate the gravitational force on two objects if we know their mass and how far apart they are, or their distance. So we can take the gravitational constant and multiply that by the two masses and divide that by the distance squared. So we can calculate the gravity between any two objects as long as we know their mass and the distance they are apart from each other. Again, gravity is everywhere in the universe. It is a universal force, no matter how far apart two objects are. The gravitational force between them never completely goes to zero. So it is a very long-range force. You have gravitational attraction to the planet Saturn. It's just not as much because you're not very close. However, there's still attraction there. So when all forces except for gravity are acting on a falling object, we can say that an object is in free fall because gravity will pull things down towards the center of the Earth. So close to the Earth's surface, when we talk about gravity and we talk about how much gravity is, the acceleration of a falling object near the surface of the Earth is about 9.8 meters per second squared. So we will use the symbol for the acceleration of gravity with a little g, and we can use Newton's second law of motion to calculate how much force is going to take to move that object. And remember, the unit that we use is in newtons when we talk about weight. So we can calculate weight by taking the mass of the object and multiplying it by the acceleration of gravity. In this case, all of our physics math problems, our acceleration of gravity, that little g, is going to be 9.8 meters per second squared. So remember, weight is a force. Mass is the measure of the amount of matter an object contains. This has been Physical Science 1, Chapter 4, Part 1 on Newton's laws.